Hello everyone. Welcome to Xdynemo. In this video, we will discuss how to perform buckling analysis on column, using Ansys workbench. We will compare the computational results with theoretical calculations. Here is the problem statement. Let us consider a rectangular steel column. Find the critical buckling load, and nature of deformation in the column, using Ansys workbench. Compare the computational results with theoretical calculations. Let us consider a rectangular column, made up of structural steel with cross-section of 150 mm by 80 mm. The length of the column is 2000 mm. One end of the column is fixed, another end is free. First, we will go through the theoretical calculations. Slenderness ratio. It is defined as the ratio of the effective length of the column to its minimum radius of gyration. Let us have a look at the data given in the problem statement. The Young's modulus of structural steel is 200 × 10⁻³ Newton per mm square. Length of the column is 2000 mm. Minimum moment of inertia is bd³ by 12, that equals 6.4 times 10⁻⁶ and power 4. Whereas the maximum moment of inertia is 22.5 times 10⁻⁶ mm power 4. For column with one end fixed, another end free, the effective length of the column is 2 times its original length. The slenderness ratio is equal to the effective length divided by the minimum radius of gyration. On substituting the above values in this equation, the slenderness ratio is obtained as 173.23, which indicates that the given column is a long column, and it fails due to buckling. Critical load. The critical load is the load at which the column fails due to buckling. According to Euler's formula, critical load is equal to pi square EI by LE squared. Substituting the above values in the critical load formula, calculate the mode 1 critical load, which gives the buckling above the axis of minimum moment of inertia. The mode 1 critical load is obtained as 789.56 kilonewtons. Now calculate the mode 2 critical load, which gives the buckling above the axis of maximum moment of inertia. The mode 2 critical load is obtained as 2775.79 kilonewtons. We are done with theoretical calculations. Now we will look into computational analysis of buckling. Buckling analysis. Buckling is characterized by a sudden sideways failure of a structural member, subjected to high compressive stress, where the compressive stress at the point of failure is less than the ultimate compressive stress that the material is capable of withstanding. Eigenvalue buckling analysis. Linear finite element analysis does not provide enough information about buckling to make correct design decisions, especially when designing lightweight components. The eigenvalue buckling mode presents the shape the structure assumes when it buckles in a particular mode, but says nothing about the numerical values of displacements or stresses. Open Ansys Workbench and create a new project. Go to Static Structural Workbench. Click on Geometry and open Design Modeler. Go to ZX plane. Change the units to millimeters. Go to Sketching and draw a rectangle at the origin. Provide the dimensions of the rectangle as 150 mm by 80 mm. Go to Modeling and select Extrude option. Click on Sketch 1 and provide the height of the extrusion as 2000 mm. Click on Generate. The geometry is ready for analysis. Close the Design Modeler. Click on Model, and wait for the geometry to get loaded into the workbench. Click on Geometry and assign the structural steel as the material. Go to Mesh and provide the element size as 0.05 meters. Right-click on the mesh and click on Generate Mesh. Go to Static Structural and insert fixed support to the bottom end of the column. Now insert force on the top face of the column. Define force using components. Provide the value of the Y component as -1000 newtons. Go to Solution and insert total deformation. Solve the model. The deformation results show the compression of column in longitudinal direction. Even if the critical load is applied, the mode of deformation still remains compression and will get the similar results. No information is available in this workbench related to buckling mode of failure. To perform buckling analysis, we have to use another workbench, Eigenvalue Buckling. Go to Solution and right-click on it. Select the option, Transfer Data to New, and click on Eigenvalue Buckling. All the data of Static Structural Workbench is shared with Eigenvalue Buckling Workbench. Go to Setup and here you can find Eigenvalue Buckling. Go to the Solution tab under Eigenvalue Buckling, and insert Total Deformation. Click on Solve. From Total Deformation results, look at the load multiplier showing the value of 792.4, which tells that the applied load of 1 kN needs to be multiplied by 792.4 times to cause the Mode 1 buckling failure. Observe the Mode 1 buckling deformation above the axis of minimum moment of inertia. Now click on Mode 2, and select Retrieve this result option. In Mode 2 buckling, the column is deforming above the axis of maximum moment of inertia. Observe the value of load multiplier showing 2777.4, indicating that second mode of buckling happens at 2777.4 kilonewtons. Let us compare the computational results with theoretical calculations. Mode 1 critical load is calculated as 789.5 kilonewtons, whereas the Ansys results show the critical load as 792.4 kilonewtons with an error of 0.36%. Mode 2 critical load is calculated as 2775.8 kilonewtons, whereas the Ansys results shows the critical load as 2777.4 kilonewtons with an error of 0.05%. Computational results from Ansys are very close to the theoretical calculations. The error in critical loads is less than 0.5%. Here are the conclusions we get from this analysis. The buckling analysis cannot be performed in static structural workbench. Eigenvalue buckling workbench is to be used. The computational results from Ansys matches with the theoretical calculations with negligible error. It is always advisable to go through theoretical calculations, or experimental data before the simulation in Ansys. The meshing and solver settings are to be modified to minimize the error. That's all for this video. If you get value from this video, please hit the like button, and subscribe to Xdynemo. Thank you. We'll see you in our next video.